Okay, now let's move on again to resolution of vector. Resolution of vector we have seen before, we will revisit it, and actually the purpose here is we saw the resolution in 2 dimensions. We'll see how we do the resolution in 3 dimensions. Actually it's just the same, only 1 dimension will be added, and another purpose is we'll have a very good revision and recapitulation of what we studied before. So I'll tell you quickly what we studied before. What we studied before is if we have an axis like this and if we have a vector, suppose r vector in this direction. Now the whole idea here is different vectors would be in different direction. If r vector is in this direction, p vector could be in this direction, q vector could be in this direction. So it will be very convenient if we break the vector in x direction and y direction, and every vector could be broken along x direction and y direction. The overwhelming desire here is if the component of q vector, r vector, p vector, they all are along x direction, then we know from the law of vector addition, if 2 vectors are in same direction, they are simply added. They are added like any scalar. So there is no vector formula of root over. The formula that we have studied is the sum of 2 vectors is a square plus 2ab cos theta plus b square. When 2 vectors are parallel, the theta is 0, so cos 0 is 1. It is root over a square plus 2ab plus b square. So basically it is root over a plus b whole square. It is actually a plus b simply. So the arithmetic, the algebra becomes very easy. The algebra actually comes down to arithmetic. So this is the motivation to resolve the vector along x and y axis. Suppose if we resolve q vector along x and y, and we get q vector is equal to qx I cap plus qy j cap, and we resolve p vector along x and y, we get px I cap and py j cap. Now if you want to add these 2 vectors, suppose q vector plus p vector, if you don't resolve it and if you simply go for addition, then you can add q vector plus p vector as we have done the vector addition before. But for that you have to look at this angle, fine, and then you have to see what angle the resultant vector makes with one of the x-axis. Then we have to see what angle the p vector makes with x-axis. Then we have to see what angle the resultant vector makes with x-axis. That's going to be a little bit cumbersome because the situation is simple. When the situation itself is cumbersome, then that addition is going to be a lot of cumbersome. So if you resolve it into components, then what you do is I cap and I cap. The components along I cap, they will be simply added. So you have qx plus px I cap because they are in same direction, and the component along j cap will be again simply added. So you will have qi plus py j cap like this, and you know the angle what the resultant vector is making with x-axis, that is tan inverse y component upon x component, that is qi plus py upon qx plus px. So the analysis becomes simple. That's why we learned it. Now what we learned before was this: how to resolve a vector. We have a vector like this, r vector, and it is making an angle theta with x-axis. Now we saw that if we make a right angle triangle like this, then this component, the base, is r cos theta. We have seen this before, so we'll spend not much time again seeing it. So rx is the component along x-axis. This is r cos theta, and the direction rx vector would be along I cap. Now you have to be very, very handy with this, because as we move ahead, I'm not going to have any discussion on this, that why the component is r cos theta. You have to be very fast and you have to develop speed in writing the component. Now you have to understand that when a vector is making angle theta with a line, then the component of that vector along that line will be the magnitude of vector times cos theta. If the magnitude is r, it will be r cos theta, and along the direction perpendicular to that line, it will be r sin theta. Now you have to be very handy doing it. The ry component will be r sin theta j cap. This is how actually we resolve it into component, and the magnitude of r vector is root over rx squared plus ry squared. It comes simply from Pythagoras theorem. In Pythagoras theorem, we know that this squared plus this squared is this squared, and this is rx, this is ry, and this is actually the magnitude of r vector. So this is rx root over r squared plus ry squared. Fine. This comes simply from Pythagoras theorem. We have seen this. Now the angle, this theta, will be equal to, if we apply tan theta in this triangle, tan theta is perpendicular upon base. Perpendicular is ry and base is rx. So theta with the resultant vector, which the resultant vector is making, if you know the j cap component and I cap component, then theta is simply tan inverse ry upon rx, j cap component upon r cap component. So you know the vector magnitude, you know the angle which the vector is making with the x-axis. So that is simple. So that's why we resolve the vector into x component and y component. So we have seen how we resolved it, and we have solved certain problems on this. Now just to inculcate a more interest in you in this vector, and actually to give you a glimpse of as to what we will study later in the course, and as to what is the relevance of the topic that we are studying now. Just to show you a glimpse, actually what will happen when we study something more, when we complete this topic and actually go into the real physics, then what would happen in a situations like this. Maybe we are given that a block is kept on a frictionless surface, and somebody is pulling this block. Maybe a string is here, and this is the angle theta which the string is making with the horizontal. Then actually you may be asked anything. You may be asked what is the acceleration of this block, or what is the frictional force, or other things, what is the tension in the string, those things. But for that, for situation like this, what we will do there is we will break this force, this tension force, the force that is applied by a person through this string, into x component and y component, and that will make things really simple compared if we don't break it into components and go ahead just considering the vector in this direction. That will become very cumbersome. So actually in a simple situation like this, things will be very simple if we break the vector into component, and it will become quite cumbersome if we don't do it. So that's why we are learning vector, breaking them into components, addition of vectors, things like that. Similarly, we will also encounter situations like this, in which maybe a block is hung from a vertical surface, maybe from ceiling, symmetrically, and then you have been asked that what is the amount of force that is being applied by each of the string. Now again, I'm not solving it now, we are not learning this because we'll go step by step, but I'm just showing you. We'll sometime ahead we'll come to a situation like this. Then again what we will do is we'll break the force of this string into components, and then we will simplify the situation and solve it easily. Similarly, suppose there's a wedge like this, and a block may be kept on the wedge is frictionless, then by the force of gravity it will come down, and you may be asked what is the acceleration of the block, or you may be asked what is the component. mg is acting downwards, force of gravity always acts vertically downwards. Now mg will be acting downwards. You may be asked what is the component of, or you may be asked what is the acceleration of the block, by what acceleration it comes downwards. Then actually gravity is acting all the time, but not entire of the component of gravity will be along the plank. Now there will be certain component of gravity that will bring it down, and there will be a certain component of gravity which will be perpendicular to the plane of motion, which will have no role in accelerating the block. So we will understand it, and again we will break the force into component parallel to the plank and perpendicular to the plank. Okay, so that's where again the resolution of vector will be used. Similarly, let me show you one more thing that we are going to study immediately after we finish vector. Suppose there's a river. And this is the direction of downstream. River is flowing in this direction. If you start swimming in this direction, then even without any understanding of physics, even a layman will tell you that you are not going to land to a point straight opposite to you on the other side of the river, because by the flow of the river you are actually will be dragged towards downstream, and you will land up somewhere here, maybe depending upon the speed of the river. Now again you would understand that when you start swimming, you maintain your velocity in the perpendicular direction perpendicular to the flow of the water. Now there is some velocity of the river that will come to you. Velocity from the velocity of the flow of water will be imparted to you through collision in this direction, and that would be done and you will be making no effort in generating this velocity, because that will be given by water to you. What you have to generate is velocity in this direction. So you will make all effort to swim in this direction, but this will be forced, this velocity component will be forcefully given to you. So we again think of it as two component of velocity, and through parallelogram of vector addition, this will be your net velocity direction, and actually you will move in this direction. So this is again where the component of velocity will come into picture. So whatever we are going to study from now, in most of the situation you have to break force, break acceleration, or break velocity, break displacement into various components. So what we are studying now is really the base foundation for what's going to come next. Okay, so you have to study it properly. So this is the resolution of two vectors that we have studied up till now, and now we will move on to study resolution of a vector in 3 dimensions, which will be pretty much the same as we have studied for 2 dimensions.